Now we have a very simple, a very straightforward question out of motion in a straight line. Now the question is actually not completely correct in terms of in wording here. Sorry for that. So the question says that a ball is thrown vertically upward with an initial velocity of 150 meter per second. The ratio of the velocity after 3 to 5 seconds actually is x plus 1 by x, and we would ask to find out the value of x. Now, when an object is projected from ground upwards with a velocity u is equal to 150 meter per second, we can write the equations of motion. The first equation of motion as v is equal to u plus at, right? And we have two instances of time here, 3 seconds and 5 seconds. So this would be v is equal to u plus at, which is a into 3. And we have v is equal to u plus at, which is 3. Okay. Now, what is a? Let's try to understand this. So, direction of motion is upwards. Acceleration due to gravity is acting downwards, which means it is opposing the initial direction of motion. And therefore, acceleration here is actually equal to minus g, which means that this is a decelerating motion. The velocity will keep on reducing as it goes up. It would come to a 0 and then come down. Okay. So v is equal to u plus at here actually transforms to v is equal to u minus gt. U minus gt. Okay. So u is 150, t is 3, times 10 is 30, 150 minus 30 is 20. So we have v at 3 seconds is equal to 120. V at 5 is equal to 150 minus g is 10, t is 5, 10 times 10 is 50, 150 minus 50 is 100, and therefore v5 is equal to 100. So we got two values, v3 over v5 is equal to 120 over 100. Now, it is given to us in the question that this ratio is equal to x plus 1 by x. So x plus 1 by x is equal to 120 by 100, which is 12 by 10. Therefore, is equal to 10 into x plus 1 is equal to 12x. 10x plus 10 is equal to 12x. And therefore, 2x is equal to 10. Therefore, x is equal to 5. Therefore, the value of x is equal to 5. Very simple, very straightforward. Just one equation of motion, and I think the only thing which could be tricky here is to choose the value of acceleration is equal to minus g. Right? And how? This is the initial direction of motion. Acceleration due to gravity is acting downwards, and since the acceleration's direction is opposite to the initial direction of motion, we take acceleration is equal to minus g. Okay, so yes, we essentially have solved the problem here. Now, we will try to solve the same question using what? It could be solved using mechanical energy conservation, or it could also be solved using work energy theorem. Okay, and I think graphical analysis wouldn't make much of sense here. But let's see if it's possible. I haven't gone through the graphical analysis so far, but yes, we have definitely gone through the work energy theorem, and we will discuss in detail how to apply work energy theorem, what is the theorem about, what is work done, what is force, what is displacement, something that I've mentioned a couple of solutions earlier, that the angle theta and the significance of it when we have theta is equal to 0 and theta is equal to 180, those things we'll try to explore here. Okay, and I can assure you that your conceptual understanding regarding work energy theorem and the application of it will become very strong. Your fundamentals would be way stronger once you follow the explanation. Okay, but again, as I do this in every question, it's a very humble request that you please write down things along with me. Make sure that you're not just buffering through the solution. You are writing down things along with me. Make at least short notes of it. Okay. Okay, now let's move on to the solution using the same question, solved using work energy theorem. Now, this is a very simple, in fact, a question which is framed in a very subtle way, but is very interesting in terms of its concept. And we'll try to solve this question using equations of motion, conservation of mechanical energy, and work energy theorem. Now, most of the books that I refer have included this question in the chapter Motion in a Straight Line under the topic Motion under Gravity, which is actually the ideal thing to do, because it really doesn't suit the kind of the genre of loss of motion or work energy power for that matter. But anyway, it's always better to explore multiple ways of looking at the question here, right? So yes, first we'll do equations of motion, work energy theorem second, and then conservation of mechanical energy. Sorry for this wrong order. It doesn't matter here. Okay, so first and foremost, let's move with equations of motion, right? Why? Because we're doing motion in a straight line. To understand the question better, the tennis ball here is dropped from 9.8 meter, which means this height here, well, I should technically be taking this very correctly as 9.8 meter. It starts from rest. Starts from rest. It will speed up slowly and will be very fast before hitting this ground. Hits the ground. Well, all of this takes place in a straight line. I've just taken 3 instances to make sure that we understand the point clearly. So it hits the ground, and when it hits, it undergoes some kind of deformation in the floor. Why? We'll come to it in a while. And after that deformation, it goes up. It was dropped from 9.8, but it goes only up to 5 meter. Now you might be wondering, since it's 5 meter here, won't it be easy to do the calculation if it's 9.8? No, well, actually it's more easier when you do it 9.8 because the multiplier becomes very easy. So the ball is dropped from 9.8 meter. It hits the ball, it squashes a little, then it bounces back up to height 5 meter, and all of this takes place, this takes place in 0.2 seconds. Or in other words, this reversal of velocity, which means it was coming down, it reverses its velocity direction, it goes up. This reversal takes place in 0.2 seconds. Okay, so the visualization of the given statement is clear, I hope. Okay, now if that much part makes sense, let us analyze each and every section of the problem given. Motion before hitting the floor. So the ball is being dropped, it reaches this point. To bring more clarity, I have dropped the point at which the ball is dropped, I have named it as A. When it touches the floor, the corresponding position as B, the velocities as VA and VB respectively. So initial position is A, VA, final is B and VB. Applying equations of motion, V square minus U square is equal to 2AS. Now what comes in? Yes, now comes the most important question here. Which sign convention to use? Well, usually in all the problems that I've done, before this, I've chosen along the direction of motion as positive and against the direction of motion as negative. So I thought of going for the traditional convention method here, which is choosing an arbitrary direction to be positive and the opposite of that to be negative. So I have taken here that the downward, okay, this shouldn't be confusing. I've taken here that the upward motion is positive and the downward motion is negative. So all the variables of the motion, if they are acting upwards, would be considered as positive. Correspondingly, would be considered as negative. Does it make sense? We'll go through in detail. Velocity of the object is acting downwards. Velocity is acting downwards. Therefore, V is negative. Acceleration due to gravity, the force of gravity will always pull the objects towards it. That will also act downwards, and therefore, acceleration due to gravity, A is minus G here. Why minus G? Because acting downwards. Downward we are taking as negative. This is the initial position, final position. Displacement vector is from the initial to the final, which means displacement vector is also acting downwards. Therefore, S is also equal to negative. Okay. So if we pull this in, if we pull this in to the equation, S is negative, acceleration is minus 10, V is negative, minus V, U is negative, minus VA. Well, to be more precise, it should be minus VA. Now, what is VA? The value of VA is equal to 0. Why is it equal to 0? Because it is dropped from rest. So what we get is minus VB square is equal to 2 into minus 10 into minus 9.8. Now, I think the way I have written this would be a bit confusing because it should be minus VB the whole square actually. Okay, minus VB the whole square. So what we get is VB square is equal to VB square is equal to 2 times 10 is 20 times 9.8 is 196. Negative times negative is positive. So VB square is equal to 196. And therefore, VB here is equal to root of 196, which is 14 meter per second. So now you might be wondering, okay, because if it's going to be squared, then it doesn't matter positive or negative. It will be equal to positive. Then why are we concerned about the sign convention here? We are concerned about the sign convention because not all equations of motion has a square in it. V is equal to U plus AT has no square in it. Does that make sense? Think of it. Write it down. Talk to yourself. Now let's see what happens after the rebound. So the ball is going up now. I have defined this as initial position B, final C, the corresponding velocities as VC and VB respectively. Applying equations of motion, V square minus U square is equal to 2AS. Again, sign convention. Now we'll have to stick to the same convention throughout the question, which means acting downwards is negative, acting upwards is positive. All the variables of motion which are acting downwards are taken as negative. All the variables of motion which are acting upwards are taken as positive. Okay, now let's see. The body is moving up, which means velocity is acting upwards and therefore velocity has to be considered to be positive. No matter what, acceleration due to gravity is acting downwards. Therefore, acceleration here will still be A is equal to minus G. Displacement vector is from the initial position to the final position, which means the initial position will have the base and the final position will have the head. Therefore, displacement vector will also be acting along the positive side. Positive. So displacement would be positive here. Okay. So bringing that in, we have displacement is positive, acceleration is negative, velocity is positive, initial velocity is VB positive. What is VC? Very important. See, VC is equal to 0. But it's not dropped from VC. Why should VC be equal to 0? Because why? Because at C, the ball comes, oops, is momentarily at rest. It is momentarily at rest at that point. So if you were to visualize this, if I drop the ball like this, it comes down here, it bounces up, it stays here for a second, and then it comes down again. Okay, one more time. A ball is dropped like this, it bounces up, it reaches the maximum height, it stays there for a second, and at that second, the ball is at rest. Okay. So since the ball is at rest at C, Vc is equal to 0, which means Vc this term is equal to 0, and therefore minus Vb square is equal to 2 into minus 10 into 5, which is Vb square is equal to minus 100, and therefore plus Vb is equal to 10 meter per second. Okay. Now, yes. Now I'm coming to it. You might feel some confusion regarding VC and VB. Let's try to understand that as well. Why do we assign direction later? What am I talking about? Assigning direction to velocity vectors later. Why? Velocity is a vector, so direction matters. But when velocity is squared, it is scalar. So direction information is lost. What are we talking about? We're talking about the idea that velocity, say v is equal to vx into I cap, for instance. What is v square? V square is actually the dot product of v and v dot v, which is vx I cap dot vx I cap, which is equal to vx into vx times I dot I, which is further equal to vx into vx is vx square. What is I dot I? It is I times cos of the angle between I and I, which is cos 0, because I is this vector. So 2I, the angle between two I vectors would be equal to theta is equal to 0. So cos 0 is 1, I into the magnitude of I is 1, magnitude of I is 1, so this becomes Vx square. So V, which was actually a vector, when squared becomes a scalar. So squaring of a vector results in the loss of the direction, the sense of direction. And therefore, we'll have to pull out that direction again. So when we calculate acceleration or change in velocity, we must bring the direction back. Why? Because acceleration is not a scalar and is a vector quantity. Falling down is taken as negative, as we have considered before, and up is considered as positive. Okay? So when the ball is moving downwards, before the impact, the velocity was positive meter per second. Oh, there is a mistake here. My bad, sorry. This would be taken as velocity coming down, which we consider as velocity at B. VB would be taken as minus 14 meter per second. Okay. And when the ball is going up, it will be taken as VC is equal to plus 10 meter per second. Impact. Okay. What? So this is before impact, and this here is after impact. Okay. Now, when we get this, velocity before impact is minus 14 meter per second. Velocity after is 10 meter per second. Therefore, change in velocity is final velocity minus initial velocity, which is 10 final minus initial minus 14. 10 minus 14 is 24 meter per second, and therefore average acceleration is delta v by delta t. Delta v is 24 meter per second. All of this happening in 0.2 seconds, so that becomes 24 meter per second. Let me just check for the consistency. 24 meter per second, which gives us 120 meter per second square. Okay. So yes, this understanding is really important here. Sign convention and applying that to the upward and downward motion. Let's now look at the same question using the concept of work energy theorem. So now we try to solve this question using work energy theorem. And when I say this, I do realize that some of us who are following the solution here would be new to this curriculum of JEE Mains and would now be started only with the first chapter, so the second chapter, motion in a straight line. So for them, this would actually be a bit of, this would be burdening. In fact, I do realize that. I'm sorry for that. Now, what am I trying to do? I'm just trying to suggest you that if you try to connect one problem in physics using multiple concepts, which you have learned in different chapters, that connecting of these different concepts, that will help you in having a concrete foundation of physics, the conceptual understanding of physics, which will in turn give you more command over the subject. Once you have that command over the subject, things are no longer hard, or things are no longer painful, or it's not a daunting task anymore. It will definitely be challenging because you're preparing for JEE Mains. Of course, it has to be, but it will be on the very lesser side of it. Okay, so apologies for taking you through two different topics which you haven't covered so far. I'll try my best to give you the brief of this. More on this when we discuss work energy power. Okay, so what does the work energy theorem says? It says work done by all forces acting on an object is equal to the change in its kinetic energy. Now, you have not learned about forces because you haven't studied laws of motion. So more of that in laws of motion. But just for the time being, understand that force is just a push or a pull. So sum of work done by all the forces. When we say all forces, it means work done by every force. So one body may be acted upon by many forces. Say it may be gravity, friction, normal force. There can be many forces. That over individual displacement. So work done by each force will be equal to force into distance, which is, F dot S, which will be force into distance into cos of angle between the force and the motion. So work done, so say for instance, there is one body like this. There is one body like this. Oops. And on this body, two forces are acting, F1 and F2. So what is the net work done? It is the sum of work done by the force F1 and work done by the force F2. What is work done by force F1? It is equal to F dot S. More precise, it is F vector F dot vector S, which is equal to modulus of vector F times modulus of vector s times cos theta, where theta is the angle between f and s, which actually is f into s into cos theta. That's what we get here. What is theta 1? It is the angle between f1 and s, to be more precise, f1 and s. And what is theta 2? It is the angle between f2 and s. It's a bit confusing, and it's not well, actually it's my bad. I should have made it more clear. Sorry for the lack in clarity there. To apply this in this chapter or this question, we analyze the complete motion into two parts: downward motion and upward motion. In the downward motion, we'll first understand what is the initial and the final position, and then we'll find out the force and displacement based on this. The upward motion, we'll have initial and the final position. We'll calculate the displacement. That times the force will give you the work done. Okay. So, part 1, downward motion. You have to find out initial and final position, corresponding displacement, and then force. Ball is dropped from a height. So the ball is dropped like this. The initial position here is A, the corresponding velocity is VA equal to 0. Force and final position is B, corresponding velocity is VB. Okay. So height is, initial position height is at 9.8 meter because the ball is dropped from that height. Velocity is 0, therefore kinetic energy is also equal to 0. So half mVA square, which is the initial kinetic energy, will be equal to half m into VA 0 square, which is half m into 0 equal to 0. Final position just before hitting the ground, velocity is v1. We don't know what the velocity is. It's v1. Kinetic energy is half m into v1 square, half m into, since it is b, half m into vb square. So we have to find out the initial and final position. Now, when this ball falls down, the change in kinetic energy, which is kinetic energy final minus kinetic energy initial. Kinetic energy final is KEB, kinetic energy initial is KEA. What is KEA? It is 0. What is KEB? It is equal to half mvb square. Now, what is this change in kinetic energy equal to? It is equal to the work done by gravity. Why gravity? Because there are no other forces acting, and the only force acting on the body is gravity. So the net work done by the forces will be equal to change in kinetic energy. Since there is only one force acting on this, the net work done will be by gravity. So work done by force of gravity will be equal to kinetic energy final minus kinetic energy initial. Work done by force of gravity is force of gravity into displacement produced by time cos theta. What is cos theta? Force of gravity is acting downwards. Displacement is acting downwards. Therefore, the angle between them will be theta is equal to 0 degrees. Therefore, cos theta is cos 0. Force of gravity is what? Force of gravity is weight of the body, which is mg. Therefore, force of gravity is mg into s. Cos 0 is 1. So, mg into s is half m into vb square, from which m by m is 1, and therefore what we get is vb is equal to vb square is equal to 2 into g into s. S is 9.8. Why? Because it is dropped from 9.8, and therefore what we get is vb is equal to 196. Vb square is equal to 196, and therefore vb is equal to 14 meter per second. Similarly, when we consider the rebound of the ball moving upwards, we have initial position C, the velocity is Vc, the final position is D, and the velocity is Vd, which is equal to 0. Why? Why is it equal to 0? Exactly because the ball is momentarily at rest. Now, in the initial condition, velocity is vc, final condition velocity is vd equal to 0, right? So what will be the initial kinetic energy? It will be equal to half m into vc square. What will be the final kinetic energy? The final kinetic energy will be half m into vd square, which is equal to 0 square, and therefore is equal to 0. Okay. So if you apply work energy theorem, work done by gravity will be equal to change in kinetic energy, which is kinetic energy final minus kinetic energy initial. Kinetic energy final is 0, Kinetic energy initial is half m into vc square. But then what is work done by gravity? Work done by gravity is gravity is acting downwards, but this time displacement is upwards. Therefore, the angle between them theta is equal to what? Is equal to 180 degrees, and therefore cos theta will be equal to cos of 180 degrees, which is equal to minus 1. So cos theta is equal to minus 1, right? Therefore, mgs minus mgs will be equal to minus half mvc square minus by minus is plus m by m is 1, and therefore vc square is equal to 2 into g into s, and this time s is equal to 5, so vc square is equal to 2 into g is 10 into s is 5, which is vc square is equal to 100, and therefore vc is equal to 10 meter per second, right? And the average acceleration calculation remains the same. Now, this time again, we'll have to pick up direction for velocity. Why? Because velocity is a vector quantity, and when we square it, that becomes, see, that explanation remains the same. So acting downwards is minus 14, going upward is 10. So 10 minus minus 14 is 24 meter per second. Contact time is 0.2, and therefore average acceleration is change in velocity by time, which is 24 meter by 0.2 second, which is 120 meter per second square. Yes, the numerical value has to remain the same. What you find out from the downward motion and from the upward motion has to remain the same. But the way you arrive at it makes a difference. Okay. So we have one more method left, which is exactly conservation of mechanical energy. So equation of motion is done. Conservation of work energy theorem is done. And now we are at conservation of mechanical energy. Excuse me. So what does conservation of mechanical energy theorem states? When only conservative forces like gravity act on a system. Now you might wonder, what is conservative force? See, it's actually a very beautiful concept, something that I don't want to briefly explain. We will go through much in depth of the concept when we discuss about the solutions to questions based on work energy power. Okay. So for the time being, let's just focus on this one. When only conservative forces like gravity acts on a system. So your takeaway is gravity is a conservative force, and when only gravity is acting, you can make use of this concept, conservation of mechanical energy. The following is true. Total mechanical energy stays constant. What is mechanical energy? Sum of kinetic energy and gravitational potential energy, or in simple terms, potential energy. Which means half mv squared plus mgh will be constant throughout the motion. What's interesting is to understand that m into g into h height, this height is measured always relative to a ground, not to a ground level. It is measured relative to any level, to an arbitrary level. Now, which any height can be taken as reference, and you'll arrive at the same answer numerically if you follow the sign convention properly. So it is your choice to choose a reference for calculating height. Would make more sense while we discuss the question, the solution in detail. So if a ball is dropped from here, you can choose this to be the reference, you can choose the point of dropping A as a reference, or you can choose the ground B as the reference, or you can even choose a point C, somewhere like this, midway, or you can even choose any point even more than that. Okay, and by all these methods, you'll arrive at the same solution. So for the ease of calculation, what I have done is I have taken the ground where the reversal of velocity has taken place as the reference height. So like we did in work energy theorem, we'll divide this problem into the complete motion into downward motion and upward motion. In the downward motion, we'll apply conservation of mechanical energy to find out the initial to final position and then find out the corresponding kinetic energy and potential energy, which was work done and displacement, force and displacement in work energy theorem. Okay. Likewise, in upward motion. So A is the initial position, B is the final position when the ball is falling downwards. It undergoes reversal of velocity. It starts moving up after the bounce. C is the initial position for the upward motion, and D is the final position for the upward motion. So far, good? Now, during the impact, when only conservative forces like gravity act, total, which is the kinetic energy, potential energy, is conserved. Net work done is zero because positive work by gravity on fall is cancelled by negative work on rise. Let us not spend much time on that. During contact with the floor, due to forces like friction, which is a non-conservative force, what does that imply? If the body is acted only by gravity, you can apply conservation of mechanical energy theorem. It holds true. But if it is acted upon by gravity and the force of friction, friction being a non-conservative force, conservation of mechanical energy cannot be applied. Why? Because some part of the mechanical energy will be converted to heat or sound or maybe light, as we see as sparks, right? So since that conservation is not taking place, well, actually, it's very simple. Since that conservation of energy is not taking place, therefore friction is a non-conservative force. Just to make it as simple as possible. Having said that, it doesn't mean we will not go through in detail. We'll go through each and every force which is conservative and non-conservative, and then we'll try to understand why are they named so. Okay. Now, coming up for the downward motion of the ball. Initial position is, wait, yeah. So initial position is A, ball is falling downwards to B, velocity is VA at A, kinetic energy is half mVA squared, and the corresponding potential energy, gravitational potential energy is m into g into HA. Now, why am I saying gravitational potential energy as if some other other forms of potential energy exist? Yes, it does. For instance, spring potential energy or elastic potential energy, to be more precise. Okay, so that's why emphasis on gravitational potential energy makes significant here. Okay. At the final position, which is at B, velocity is VB. Kinetic energy is half mVB squared. And the potential energy is mghp. And references this level where the ball is bouncing, where the ball is hitting the ground. Okay. Now let's apply the conservation mechanical energy statement here. Initial kinetic energy is half mVA squared. Initial potential energy is mgh into mgha. Final kinetic energy is half mvb squared. Final potential energy is mgh into hp. In this, velocity initial is equal to 0. Therefore, this term becomes 0 plus. HB. HB overlaps with the reference height h equal to 0. Therefore, HB is also equal to 0, which means this term is also equal to 0. So this becomes plus 0, which gives us mg into 9.8, which is HA. Why HA is 9.8? Because the ball is dropped from a height. The ball is dropped from a height. H is equal to 9.8 meters. So what we get here is mg into 9.8 is equal to half mvb square. M by m is 1. And we have 2 into g 9.8 is vb square. Vb is 14 meter per second. Right? Now, again, what happens during the upward motion? Initial position is C, final position is D, corresponding velocities are Vc and Vd, corresponding kinetic energies are half mv Vc square and half mvd square, and the corresponding heights are mghc and mght. Okay? And the reference here is h equal to 0, which is the ground, which means exactly hc should be equal to 0 here. And the ball is rebounding and it is rising to 5 meter. Therefore, HD should be equal to 5 meter here. Right? So, if we apply the conservation of mechanical energy statement here, initial kinetic energy half mvc square, initial potential energy mg into hc is equal to half mvd square plus mg into hd. What is hc? It is 0. What is Vd square? Vd is 0, therefore Vd square is also 0. Why is it 0? Because the ball is momentarily at rest. And why is it momentarily at rest? As we discussed earlier, the ball, it falls like this, it bounces back, it stays up in the final position for it was dropped from 10 meters, it hits the floor, it bounces back and reaches the maximum height. At that height, it stays there for a moment and then comes back. At that moment, it is at rest, which gives us half mvc square is equal to m into g into hd. hd is 5, g is 10, m by m is 1. So we have vc square is equal to 2 into 10 into 5. Vc is 10. And the calculation remains the same. Again, bring up direction. Why? Velocity is a vector. Acceleration is a vector. Average acceleration is a vector. Bringing up velocity, taking downwards as negative, upwards as positive. V1 is equal to minus 14. V2 is equal to plus 10. Delta V is V2 minus V1. 10 minus minus 14, 24. Time is 0.2 seconds, which is 120 meter per second square as average acceleration. One problem, 3 different solutions, same answer. 3 different concepts, same answer. Now you are more confident at the same problem. How? You are confident at the same problem, but you have strong concepts in 3 different chapters. Okay? Well, technically 2 different chapters. Motion in a straight line and work energy power. Okay, so that was the story with conservation of mechanical energy. Now let's take a break and maybe let's do some questions on, or maybe let's focus only on motion under gravity. Motion under gravity.